Episode of Mr. Avila Physics. Today we're going to be talking about continuous charge distribution. Right, and we're going to start by seeing how this continuous charge affects the electric field, or actually the other way around, how we can find the electric field due to a continuous charge. Up until now, we have found the electric field caused by a point charge. But in many cases, we don't have a point charge. We have a charged object, like a ring or a wire or a charged plate, right? And in those cases, the charge is distributed evenly and continuously throughout the entire object. So how do we analyze situations like this when we only know how to deal with point charges? Well, what we do is we take the object and we break it down into an infinite number of pieces of differentials, right? And each one of those differentials is going to have a piece of the total charge. And that piece is going to be dq, right? A charge differential. And then that charge differential is going to create an electric field differential at a distance r, right? And that electric field differential is going to be equal to K dq over r squared, right? Now, so what we're going to do is we're going to take each one of those, pieces and find the electric field created by each piece, and then we're going to add all these pieces together through the integral, right? So to find the total electric field created by a object with continuous charge distribution, then we're just going to integrate the sum of all the electric field differentials. Let's look at an example. Here we have a ring-shaped object of radius a that has a total charge plus q distributed uniformly around it. Right? If I want to find the total electric field at point P, then let's see what we have to do here. Okay, so what we have here is we have a little piece of the ring, right? A little dl. Now this length differential has a charge differential dq. And this charge differential dq is going to create an electric field differential dE, right? Now, if we notice this electric field differential is at an angle, so it's going to have a horizontal component and it's going to have a vertical component dy. Now, all the charge differentials are going to have things like this, right? So if we look at, say, this length differential exactly below the one that we analyzed, and we look at this dq, then this charge is going to create an electric field differential over here. And this one is going to have a horizontal component and a vertical component. Now, what do we notice here? We notice that the vertical components cancel each other out. So if I look at this length differential and this length differential, same thing is going to happen. If I look at this length differential and this length differential, same thing is going to happen, right? All the perpendicular components are going to cancel each other out. So if I know that the electric field is equal to the integral of the electric field differentials, then this is also equal to dx plus dy. But I know that all the perpendicular components of the electric field cancel each other out, and this goes to 0. So that means that the electric field is going to be equal to the integral of dx. So this is like this, right? And the electric field differential is equal to K dq over r squared cosine theta. Now, if we look at this formula, it's going to be very hard to integrate because we have different variables. We have dq, we have theta, right? And our differential is of length. It's dl, right? So it's kind of hard to integrate unless we can put all of this together, right? So let's see if we can express things in different terms. Now, here we have that lambda, right, is equal to the charge density, right? The charge per unit length, which is coulombs per meter. So I can say that lambda is equal to Q over L, right? Charge over length. But this ratio is a constant. So lambda is also going to be equal to dq over dl, right? Which means that dq is going to be equal to lambda dl, okay? So I can make that first substitution for dq. And since the angle doesn't change, right, then I can also say that cosine theta is going to be equal to adjacent over hypotenuse, and this is going to be equal to, right, x over x squared plus a squared to the power of 1/2. All right, now with this in mind, let's continue working on our solution. Okay, so that means that, okay, the electric field is going to be equal to the integral of k dq over r squared cosine theta. So that means that the electric field is going to be equal to k lambda dl over r squared times cosine, which is x over r. So our electric field is going to be equal to the integral of k lambda x dl over r cubed. Okay, now what's going to be our boundaries for integration? Since we're integrating all along the length of the ring, then the length of the ring is going to be its circumference, right? So then our integral is going to be from 0 to the circumference 2 pi a of k delta x over r cubed x squared plus a squared to the 1/2 cubed dl, right? We take out our constants. That means that the electric field is going to be equal to k lambda, which is a constant, x is a constant, right? Our radius is a constant as well. So our only variable will be dl from 0 to 2 pi a. And we integrate and we get that our electric field is going to be equal to k lambda x 2 pi a over x squared plus a squared to the power of 3/2. But we also know that lambda is equal to q over L. So lambda is equal to q over 2 pi a, which is the length of the ring. So that means that Q is going to be equal to lambda times 2 pi a, which means that our electric field is going to be equal to KQX over x squared plus a squared to the power of 3/2. Ta-da! So that would be our answer right here. How can we kind of tell if this makes sense? Well, what happens when x becomes really large, right? X is way, way larger than a. What happens here? We get kq over x squared, which is the electric field created by a point charge, which kind of makes sense because at very, 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 very large distances, a ring will seem like a point charge. All right, let's look at another example. Okay, here we have determine the magnitude of the electric field at any point P at distance x from the midpoint of a very, very long wire. Right, this wire is continuously charged with a positive charge Q. Assume that x is much smaller than the length of the wire and let lambda be the charge per unit length, coulombs per meter. All right, so let's look at this problem kind of like the same way that we looked at the other problem. Okay, so here we're going to take our wire, we're going to split it up into little pieces, dy, right? And this dy is going to have a charge differential dq. This charge differential is going to create an electric field differential, right? Which will have a horizontal component and a vertical component. Through symmetry, we can see that if I take this length differential right here, it's going to create an electric field in this direction, which will have a horizontal component and a vertical component, and the vertical components will cancel each other out, and that will happen all along the wire for things that are equidistant from the midway point, 0. Okay, all right, so same thing. I know that my electric field is going to be equal to the integral of the electric field differential, which is going to be equal to the integral of dx plus dy. This cancels out, so that means that our electric field is going to be equal to the integral of dx, which means the integral of dE cosine theta, which means that this is k dq over r squared cosine theta. All right, so similar to our previous example, we have to kind of figure out our variables. So here I know that lambda is equal to q over L, which is equal to dq over dL, which means that the charge differential dq is going to be equal to lambda dL, right? I also know that, right, r is equal to x squared plus y squared to the power of 1/2, but in this case r is not a constant because as we move our length differential to different places, r changes as well as theta. Okay, so different variables here. All right, so that means that our electric field will now become the integral of k dq over r squared cosine theta, which is equal to the integral of k lambda dl, in this case dy, right, over x squared plus y squared to the power of 1/2 cosine theta. Now here we have two options. We can either change theta in terms of y, or we can change y in terms of theta, right? Either one. So I'm going to go with the second option and go with y in terms of theta. Y, I don't know. I just like it better that way. You can also try it by changing theta in terms of y and see what happens. All right, so to change y in terms of theta, I'm going to look at our triangle here and see that y, let's make a little pause here, see that y is going to be equal to x tangent theta. Based on our triangle right here, right? Tangent theta is going to be equal to opposite over adjacent, y over x. So that means that y is going to be equal to x tangent theta, which means that dy is going to be equal to x over cosine squared theta d theta. Okay? And I also know that cosine theta, right? Cosine theta is going to be equal to adjacent x over r. So cosine theta is going to be equal to adjacent x over r, which means that r is going to be equal to x over cosine theta, which means that r squared is going to be equal to x squared over cosine squared theta. Right? Which means that I can now change our variables. So that means that my electric field is going to be equal to the integral of k lambda dy is now x over cosine squared d theta, right? And r squared, which is this term right here, is equal to x squared over cosine theta. So this would be x squared cosine theta, and then our original cosine theta, this cosine theta right here. Okay? Simplifying this, we get that our electric field is going to be equal to the integral of k lambda cosine theta d theta over x. Okay? So it's going to take out our constants, k lambda over x. It's the integral of cosine theta d theta, right? Now, what's going to be our integration boundaries? Well, if the wire is very, 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 very long, then if we look at the tip of the wire and draw a line to the point P, it's going to look almost like a vertical line. So I'm going to be integrating from minus pi over 2 to pi over 2. So that means that my electric field is going to be equal to k lambda over x times sine theta evaluated from minus pi over 2 to pi over 2. So this is going to be equal to k lambda over x times 1 minus k lambda over x times negative 1. So electric field is equal to 2k lambda over x. And this was the second example of finding the electric field due to a continuous charge distribution. All right, let's look at this third example right here. In this third example, we're looking at a charge is distributed uniformly over a thin circular disk of radius r. The charge per unit area, coulombs per meter squared, is sigma, and calculate the electric field at a point P on the axis distance c over its center. So for this one, since we have a charged area, we cannot break it down into little length differentials. We have to break it down into little area differentials. And if we look closely to this circular disk, we can break it down into an infinite number of rings, right? Each ring has a width of dr, and it spreads from 0 to r. Now, we already found the electric field due to a charged ring in the first example that we saw. So we can take that answer and integrate that from 0 to r. So in this case right here, this right here is our answer from the first example, right? Just substituting the correct variable, right? So we would substitute x for z and a for r. And then, right, we would just integrate this from 0 to r. Okay? But first, we would have to change, of course, our dq differential into a dr by using our definition of charge distribution, okay? Which is this one right here. Sorry about the missing the square bit right here. So once we change our dq into sigma 2 pi r dr, then we can integrate from 0 to r and get our answer. Cool. All right. Now, let's see how this relates to potential, okay? So, once we have the electric field, then we could find the potential because there's a relationship between potential and electric field that we learned in a previous video. But sometimes we do not have the electric field, or it is difficult to find, like we just saw in the previous 3 examples. But we can still determine the potential between 2 points using the integral of electric field dl, right? So if we do not know E as a function of x, then we can still find V by doing kq over r. So kq over r is the potential due to a point charge. So if we break that point charge into a charge differential dq, then our potential becomes k dq over r. And then we can just integrate all that. All right, let's look at an example, okay? So a thin circular ring of radius r has a uniformly distributed charge q. Determine the potential at point P on the axis of the ring at distance x from its center. Now, in this case, okay, we don't have to worry about components or anything like that because this is potential, right? So potential is a scalar quantity, so we don't have to worry about components, symmetry, and all that. So we just have to find out our potential due to each charge differential, okay? So in this case, right, just to recap what we just saw, we know that potential is going to be equal to the integral of k dq over r. K and r are constants, right? So this is going to be equal to the k over r times the integral of dq. And we're going to integrate along the entire total charge from 0 to q, right? So when we integrate this, there we have it, okay? We have our potential, which is going to be equal to kq over r, evaluated from 0 to q, which is equal to kq over r, right? Which is equal to kq over x squared over r squared to the power of 1/2, which is our answer here. Remember that this is k, okay? And if x is way larger than r, then this reduces to kq over x, which is the definition of potential due to a point charge. All right, let's look at another example. Right, here we have a flat disk of radius r0, which has a uniformly distributed charge q. Determine the potential at point P on the axis of the disk, a distance x from its center. Now this one's a little bit different because we cannot break this area into tiny point charges. We have to break it down into tiny area differentials, right? So we know that the total area, right? The total area has a total charge Q, which means that an area differential dA would have a charge dQ, right? I know that the total area of this disk is equal to pi r0 squared, right? And this has a charge of Q. And the area differential, right, this little ring right here is going to be equal to the circumference times the width of the ring. So this is going to be equal to 2 pi r times the width dr, and this is going to have a charge differential dq. Solving for dq, I get that dq is going to be equal to q times 2 pi r dr divided by pi r0 squared. Simplifying a little bit, I get that dq is equal to 2q r over r0 squared dr. Now that I have an expression for dq, now I can find my potential, right? I know that potential is equal to the integral of k dq over r, which is going to be equal to k times the integral of dq over r, which is x squared plus r squared to the 1/2. In this case, r is not constant because as we express our ring differentials from the center to the end, then r changes. So this is going to be equal to k times the integral of 2q r over r0 times x squared plus r squared to the power of 1/2 dr, and we're going to be integrating from 0 to the entire disk, which is R0. Taking out the constants that I can find, it's going to be 2q times k over R0 squared times the integral from 0 to R0 of R over x squared plus R squared to the 1/2 dr. Right? This right here is u to the n du, right? So I can use the laws of integration that I need, and this equals to 2qk over R0 squared times 2 times x squared plus R squared to the power of positive 1/2 divided by 2, evaluated from 0 to R0. Simplifying and substituting R0 and 0, I get an answer of 2qk over R0 squared times x squared plus R0 squared to the power of 1/2 minus x squared to the power of 1/2, which is x, minus x. And this becomes the potential of a charge plate. All right, okay. Lots of examples today, very long examples. So I apologize for the length of this video, but I want to thank you all for watching, and I'll see you next time.